previous test, I want to briefly discuss solutions to the second and third exercise. So the second exercise was the number of derangements of words A, B, C, D, E, F. Okay, so first of all, if we assume that these letters are different, then we should get D7 number of derangements. But some of these derangements will not be derangements after we say that they're the equal letters. So we need to subtract the number of derangements which are not derangements. And there are exactly 3 types of such permutations. So first of all, we need to look at this type of permutations where A2 goes on the first place, A1 goes on the second place, and then here will be the derangement of these 5 letters. Because it is the usual derangement for if they're distinct, but if they're non-distinct, then there will be not a derangement because he will be A and he will be A. So this will be D5, yes? And there are another two cases when on the first place will be A2 and A1 will be somewhere here. And symmetrically, A1 is here and A2 somewhere here. Okay, yeah. And if you look at these permutations, then here, so A1 should not be placed on the second place, and so we have 6 letters A1, B, C, D, E, F, and this, so none letter will be staying on its position. So this is just the derangement of 6 letters. So here is the 6, and this is the 6. These permutations are not intersect to each other, so we can just write D7 minus 2 D6 minus D5, but also we need to, if you want to make a distinction between A1 and A2, then we need to divide over 2 this number of permutations, because we can change in each of these. Yeah, because when we count this guy, we assume that A1 and A2 is distinct, and in derangement they're non-distinct. So we need to divide this over 2. So some of you divide it over 2D7, some of you count this guy but not divide it over 2. So there were no correct answers to this problem. Okay, and about the third task, so we have there something like, the picture was something like this. So it's called arc diagram. And the easiest way to find the answer is firstly so we need to, we have 2n elements, and we need to connect them with pairs. So we need to calculate how much pairs can we make from these 6 elements. So we have, if we have n pairs, let's assume that we have n different colors, and we want to calculate how much colorings are there of these 2n points, such that each color, so there are 2 elements for each color. So for example, I can look at all colorings where there are 2 orange, 2 green, and 2 blue elements. This is just the multinomial coefficient m of 2, 2, etc. 2, because I just have this n times. Or you can just say that we just choose the 2 elements for the orange, 2 elements for the green, and 2 elements for the blue, and there are 2n choose 2 elements for the orange, 2n minus 2 choose 2 for the green, 2n minus 4 choose 4 for the blue, and so on. And this is the same. But if we provide the arc diagram, then we can forget about colors. So if I change orange colors and green colors, so pairs of orange and green, the arc diagram will be the same. Yes? So we need to divide this over n factorial, all the permutations of these n colors. And this is the correct answer. So the correct answer will be 2n factorial divided by n factorial and 2 to the power n. And again, some of you find the 2n factorial over to the n power. Some of you find 2n factorial over n factorial. So there are you have partial solution, but I think there are only 1 or 2 correct answers in this problem. This is not very hard. Yeah. Okay. Okay, there was one question about the homework, and I will answer it now. About the homework, let me find it. 1 minute.
Hello, Professor.
Yeah, hello.
Can we give the answer n factorial plus 1 for question number 3?
Sorry, for this problem?
Yes.
N plus 1 factorial?
No, n factorial plus 1. It works for 4 dots. It works for 6 dots.
Yeah, but it's not. But I think for 6 dots you will have. So let's calculate. So for n equal to 3, this will be 6 times 4 over 8. This will be 15, and 15 is not n factorial plus 1. Or if I yeah, okay, so the question about the exercise 6, so there we need to find 5-digit codes. 5-digit codes which have 3 and 5. And so the correct solution will use the inclusion exclusion formula for it, but there is. So I will explain you the solution, and you'll tell me what's wrong in it. So first of all, we choose 2 positions for 3 and 5. So we have 5 places, and we choose 2 positions for 3 and 5. So we put here 3, put here 5, and put take any number to other 3 positions. So the answer will be 5 times 4 times 10 to the power 3. So you choose the positions for the 3, choose position for the 5, and then fill other positions in for take any number for other positions. Why is this incorrect? No, because the correct answer is when you. So if you want to calculate it, you just take the all digit codes, which is 10 to the power 5, and then you subtract. So you need to have 3 and 5. So for example, if you need to have only 3, at least one 3, then you just can subtract the number of digit codes which doesn't have 3. So this is all codes and codes numbers. Where are codes? All numbers. No, not. Okay, let's write codes. No, what was in task here? Oh, sorry. Okay. And then, for example, if you forget about 3, then you have 9 to the power 5 if without 3. You have 9 to the power 5 without 5 and 8 to the power 5 without 3 and 5. And so you take all the codes and you just cut out subtract the number of codes without 3 and without 5, and then you add the number of codes without 3 and 5. Yes. But this is different answer. Why is this incorrect?
Because 3 can be in other position.
Yeah. So for example, if these digits are not 3 and 5, then in this case it is okay. But if you put here, for example, 3 and something like 7, 8 here, then so you count this code twice because you have 3 on this position, 5 on this position, and 3 other digits, and you have 3 on this position, 5 on this position, and 3 other digits there. And so you calculated this combination twice, and so some combinations account once, some combinations account twice, and so this answer is incorrect. Okay. Okay, and about your question. So again, what if we have linear calculations but non-homogeneous with some constant? You solve this in 2 steps. First, find partial solution. Why is it so important? Because if you find partial solution, then 2 solutions differ in solution of homogeneous recurrence relation. So if find one partial solution, then all other solutions we can find it by using formula. So if you find partial solution Bn, then we can solve homogeneous. I suppose this is correct. Linear recurrence relation, and so for example, in this case, it will be a times 1 plus squared over 2 to the power n plus p to 1 minus square root of 5 over 2 to the power n. Yes, something like this. So if you solve this, then the answer is bn plus a times 1 plus square root 5 over 2 to the power n plus b to 1 minus square root 5 over 2 to the power n. And so if you have for initial elements, you just take n equal to 0 and 1 and find a and b by these constants. But the important part is you need to find partial solutions. How you can do this? In this case, you just can. No, there's several different approaches. First of all, you can just take, for example, a0, 0 and a1, 0 and try to find what will be n. Maybe it's not so hard to find it. But if you find the let's say stable solution, you can see that if I start with so I can rewrite this as an minus 5 equal to an minus 2 plus n minus 1 plus n minus 2. And if I start with minus 5 and 0, no, minus 5 no, it's work for the minus 5, I suppose. Maybe minus 5, 0, 0. No, I don't. Okay. Yeah, suppose that we need to just take a0, a1, 0 and try to find formula for the bn and then find a and b just using the initial terms of this sequence. Okay? And what's your question? So what do you understand? Okay. So you take a 0 and a 1, 0, then we'll have 0, 0. We can just look at the first several terms here. 0, 0, 5, then so we need to 20, 35, and so on. So if you divided this by 5, because all this is divisible by 5, you can see that this reminds you of the Fibonacci numbers minus 1, yes. So if you take dn is fn minus 1, then dn minus 1 plus dn minus 2 will be fn minus 1 plus fn minus 1, which is fn minus 2. And so if you write this plus 1, then it will be fn minus 1 and bn. So is this a solution for where the non-homogeneous part is plus 1? But if this is plus 5, you need just multiply it by 5. So the partial solution Bn is 5 times Fn minus 1. Okay? How I get this? So Bn minus 1 plus Bn minus 2 plus 1 is Fn minus 1 plus Fn minus 2 minus 1. I just use this formula. Then the sum of Fn minus 2 and Fn minus 1 is Fn. And here I have minus 2. So if you have here plus 1 here, then it will be just Fn minus 1, and this is equal to Bn. Okay. Yeah. Maybe it's I don't know. Maybe it's a trick, but I don't forget how to get it. What I can say that another partial solution. Yeah. Sorry. So this is just one strategy, and another strategy. First idea is to find constant solution. Constant solution, that means that an is the same number x. So you have equation x equal to 2x plus 5. So x equal to minus 5. And so if you start with a0, a1 equal to minus 5, then all an equal minus 5 is partial solution. So, and because of course this must be any solution of the homogeneous part, and so we can take zeros as homogeneous part. So you can just take here minus 5, because of course Fn can be put in here. Sorry, just forget about how to get the constant solution. Okay. Any questions? Let me. Yeah, I just need to open. Okay. The last problem was, so we need to calculate the number of permutations with no two consecutive numbers. Did someone find the formula for this? No? Did someone solve it? Yes? Could you explain it? No. Yeah. Okay. Okay. Yes. Um, so we denoted by AI the number of permutations. AI permutations where I plus 1 consecutive. Yes. And how to calculate the number of elements in AI? For example, A1. No? You do it like this? No? How? Could you go to the board? No? Go explain the solution. Okay, who else can explain the solution? Yeah. Okay. 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 Yes. Okay. How many permutations do you have when you have one pair? Why? So, for example, if you want to calculate the number of A1, you just, so the number of permutations we will have 1 and 2 to be consecutive. You just suppose that there are one number, so you have 5 places, and in one places you put 1, 2, and the other places you fill with other numbers, yes? Okay, there will be 5 factorial such permutations. Yeah, so it is for A1, and of course, if you summarize for all AI, there will be 5 times 5 factorial. Okay, now about yeah, so the problem is when you calculate the number of the pairs, you have to consider 2 different cases. If there are 3 consecutive numbers, so for example, I plus 1, and I plus 2, and if they are disconnected, so we have, sorry? Yeah. So if you so for example, if you have two different pairs named 1, 2, and 3, 4, then you have 4 different positions. Where you can, for one position, put 1, 2, the position put 3, 4, and in this case. In this case, is 1, 2, 3, and the same, you put this in one position, and another 3 digits numbers you put in other 3 positions. So this will be 4 factorial, yes? And I think the same holds for the triple intersection, because if you look at the triple intersections again, you just glue. So every time we have one number less, because we glue some numbers together, and so the numbers that are left will be 3 factorial, 2 factorial, 1 factorial. So the answer will be something like 6 factorial minus 5 times 5 factorial plus 5 to 2 times 4 factorial. Yes? Minus 5 plus 3 times 3 factorial. Something like this. Yeah? Okay. Sorry? Okay, so maybe again you can solve it by the recurrence relation, but if I find it in the break, I will discuss it with you, because I just I need to be okay. I just don't forget. I don't remember the solution right now, so I think we should continue. Yeah. Yes. It would be at an equal to n minus 1 times an minus 1 plus n minus 2 times an minus 2. This? No, sorry. This? Yes. Something like this? Okay, how do you get it? Why do you have such number of how to get this formula? Okay. So I suppose you just need to again look at the you look where you put, for example, first number. I don't know. The idea, I think that you just look at such permutations where so no, you just look where you put number 6, and then you have, so for example, of course, if 6 in the first position, then you just need to calculate the Fi. Because you just look at all permutations of 1, 2, 3, 5 with no two consecutive numbers. But if 6, for example, in the middle here, that you need to calculate all such permutations where 5 is not here. So if 5 is not here, it is still a 5. And if 5 is here, then you need to calculate the number of so we need to calculate this type of positions and subtract it from the all previous ones. Okay, but okay, let's maybe during the break I find the short solution, but I can remember it right now. Okay, let's continue to discuss the topic from the previous lecture. So we discussed the Catalan numbers, and we have different definitions: the number of triangulation of polygon, the number of paths from 0 to n over the diagonal, the number of correctly matched pair of brackets, and the number of binary trees. So first of all, I want to prove the formula for the Catalan numbers, because we discussed that we have the recurrence relation that looks like this. You need to calculate the product of previous elements and summarize them. But of course, we want to give the short formula to find the Catalan numbers. So this is not, this is not very easy, but it's still not very hard to obtain a formula. But we need to do some tricks, and so I'll give so I'll finish the first trick, and the second trick I'll try to give you an idea, and then you can just, if you want it, you can think about this idea and how to calculate the number of the form of Catalan numbers in different ways. So the trick that I will do is called reflection method. And we will use the definition of Catalan numbers using path. And then I will write the grid. And then so we look at all the paths that goes from 0, 0 to n and goes over the diagonal. So for example, this one is good. And this grid is useful because we know if we forget about this property, so how many number of paths from 0, 0 to n if you're going only up and right? Do you remember the formula? All paths going up and right from 0, 0 to n. Yeah, why is it so? The answer is to n choose n. Why? Yes. Yeah. Yeah, so we have the sequences of going ups and rights, and you need to be exactly n of them to going up, and this is exactly the number of combinations. And if you're going from 0, 0 to kn, then the formula will be k plus n plus n the same way. We use the same idea. So you're going k plus n steps, and exactly n of them should be up or right. So here is up. Exactly n of them should be up. This is exactly the number of combinations. So we want to correlate it, the path that goes only above the diagonal to the path that going with path that going exactly all paths from some points to another point. And the idea, so we'll try to draw a picture here. So let me make a suggestion, and then so I just want to be sure that I do the reflection right. This is not. So I want somehow to look at this path and reflected the first parts to the first intersection of the diagonal and reflected like under the diagonal. And how I can do it? Let me see the picture. Because in my mind it is going under the diagonal and it's kind of oh yeah, okay. So we have totally 2n choose n number of paths. So if you want to calculate the Catalan numbers, we just need to calculate the number of paths that are going under the diagonal. So let's look at the paths that are going under the diagonal. So for example, I want to look Sorry. So for example, something like this. And so what's the property of this path? This path always intersect the shifted diagonal which is the line y equal to x minus 1 plus 1 minus 1 minus 1. X minus 1. And so we take the first time this path intersects this line, and the all path above it, we reflect it with this diagonal. So reflection is going like this. So I want to prove that, so if I reflect this over the diagonal, then I will end not in point n, but at point n minus 1, n plus 1. And I want to prove that I have one-to-one correspondence between all paths from 0, 0 to n1, n minus 1, n plus 1, and all the paths from 0, 0 to nn that goes under the diagonal. So I want to prove that there is a bijection path from 0, 0 to nn going under the diagonal, usual diagonal, and just all paths from 0, 0 to n minus 1, n plus 1. So this is, so what I give you is just the mapping from first pass to second pass. So all paths that goes under the diagonal, they will intersect the diagonal y equal to x minus 1. And from the first intersection, I will take reflection over this line. And I will end into n plus 1, n minus 1. Or the other way, if I started in 0, 0 and finished in, so if I started in 0, 0 and finished in here in n minus 1, n plus 1, then I can take, so how can I get this path? I will draw all the diagonals. Oh, sorry.
Professor?
Yes.
And what is the use of a reflection of the path? I mean, why did we do that?
Because we don't know how to calculate the path that's going under the diagonal, but we know all the paths that are going.
So and what does it mean that the path under the diagonal. What should we calculate? What is that number?
Okay, so we have the total number of paths going from 0, 0 to n. And
Yes.
we want to find the number of Catalan numbers. The Catalan numbers is the path that are going of the all paths going over the diagonal. So if we subtract it from 2n choose n, then all the left is the path that going from 0, 0 to n and somehow going under the diagonal. So we need to calculate this guy. And we don't have formula for it. But if I prove that this is a bijection between these two guys, I know how to calculate the path from 0, 0 to n minus 1 and plus 1. This is just another binomial coefficient 2n choose n minus 1. And if I prove this, then I will prove that Tn is just 2n choose n minus 2n choose n minus 1. And this is the formula for the number of Catalan numbers. But I need to prove, with this reflection method, I want to prove that there is a projection between path from 0, 0 to n that I somehow, in some time, going under the diagonal, so they intersect the diagonal and going under it, and all the paths from 0, 0 to n minus 1 and plus 1. So we just need to roll the same line. Y is equal to x minus 1. And then our line will always intersect it because the point stated on the different sides of this line. And so there will be always intersection here. And we again reflected all the path, this path after this intersection by this diagonal. So we get something like this. And so this is the path from 0, 0 to n. So for each path from 0, 0 to n minus 1 plus 1 will be intersecting the diagonal. We take the first intersection and then reflected the second part of the path over this diagonal. So we do nothing but reflection over the line. So it's easy to see that this mapping inverse to each other. And so for each touch path we have for each path that's going under the diagonal is the corresponding path that's going from 0, 0 to n minus 1 and plus 1. And to the other hand, we have the inverse mapping. It's easy to see that if we reflect this way, then the reflection will be inverse to each other. So this proves that the formula for the Catalan numbers is 2n to n minus 2n to n minus 1. And this is just the we can simplify this formula to this is 2n factorial over n factorial minus 2n factorial n minus 1 factorial n plus 1 factorial. So here I have how can I simplify it? I need to write n plus 1 here and here. It will be 2n factorial n factorial n factorial. So I multiply it by n and put the n plus 1 over here. And this is equal to 1 over n plus 1 of 2n choose n. So we get the formula Tn is equal to 1 over n plus 1 times 2n choose n. So for example, if we look at these three, it will be 1 over 4 of 6 choose 3 at this is 20. So it's 5. Yeah, this is correct. So for example, for n equal to 3, this coincides with the formula. Okay, do you understand this, or do I need to maybe write different pictures here? So I can, if you want illustration for the reflection method, so for example, if I have I can just draw different pictures for the different paths going from 0, 0 to 3, 3 going under the diagonal. So for example, for this guy, I need to, so I just take this intersection and then I reflect it. Then I will be going like this here. If it is going this way, then, for example, I just again draw the diagonal and symmetrize only this part. I know, so I think it is, you can write the pictures and check it yourself that for example, for this guy will be again write the diagonal and reflect it here. So for each path that goes under the diagonal, I will link to the path going from 0, 0 to n plus 1 plus 1. Okay. Questions? So another approach to, so I'll give you another idea of approach and then we'll have a break. Another idea, if we look at correctly matched brackets, then we want to try to code it. So if let's illustrate the correctly matched pairs of brackets as the different number of how can we make the multiplication of elements. So I will put some element a inside the brackets. So for example, if we have for a's, then we can, how can we calculate multiplication of it? We can take the order of multiplication can be given as exactly the Catalan number of 3. We can yeah, something like that, if I don't mistake here. So I want to do this. So I want to write a code for this multiplication. And the idea that I will provide is the algorithm. So if I have, so if I need to multiplicate the words u and v, I will write the multiplication to the right of it. So I will change it as U, V, and symbol P. What does it mean? So for example, if I have one pairs, only a multiplication of AA, then this will be AAP. So I multiply two elements, then I just wrote this as AAP. If I have 3 elements, then I will have, so this will be AAP times A. So I need to write this as AAP, AP. This will be A times AAP, which is AAP. So I take the first word, try the second word, and wrote P after that. So for example, for this guy, this will be A times AAP. This is AAP, something like this. And for example, for this guy, I should write A times AAP times AAP, AP, and AP. So I will be getting some different codings with A's and P's. I will have exactly 4 A's and 3 P's. But of course, I non so not for every sequences of 4 A's and 3 P's, I will have the inverse image, inverse mapping. So I need to find the properties of such sequences of A's and P's such that they correspond to correctly match sequences of brackets. And so the main proposition is that so I need to somehow get from this explanation the number of 1 over 4 of 6 choose 3. Yes, so first of all, I need to get rid of some element of first element A, because the first element will be always in this explanation, first element will be A. So and then I want to say that for each of these sequences, there are exactly 3 different sequences that correspond to this one, this one, this one, and they will be covering all different combinations of 3 letters A and 3 letters P. And let me. So I want to give you the correct proposition. Okay. Maybe I want. Okay, let's do maybe. So if the previous method will be called reflection method, then I think that this idea is called something like rotation method. Because so the main tricky proposition is that if I look at this sequence and I will make so I will be rotated or just change it by I don't know. If I imagine that I wrote this element into the circle and then I rotate it, then I will have different sequence. So for example, if I have A, P, then I will, if I know how to call it. So in different literature, it's called circular shift, something like that. Circular shift. That I just move the last element in the first position. I will get this guy, then this guy, and then this guy, and so on. So each of these sequences can be shifted or rotated, and I want to prove that I always get different different sequences. So how to get this proposition? For each sequence of let's denote something. So here I have n2 n brackets. Then I have n plus 1 and n p's. So for each sequence of n plus 1 a's and n p's, there is one and only one shifted sequence which can be obtained from correctly matched brackets. So I illustrate it on the, so for example, for the 2 A's and 1 P, there exactly only one. So circular shift will be getting this way, and so I'll have only one element. So if we have 3 A's and 2 P's, then the picture will be as following. So I have, if I rotate this, I will get A. So I have, so if I make a circular shift, I will return to the first sequences in 5 steps, and so I have this guy as can be obtained from Stockholm image bracket, and the second one is just all the sequences where I have two consecutive P's here, letter of P. So I have exactly 10 possible ways of choosing 3 A's and 2 P's, and in each it's called, I know it's the group theory, it's called the orbit. So in each orbit of this rotations, under the rotations, I will have exactly one element that corresponds to the correctly matched pairs of brackets. So if I prove this proposition, then I get the formula that the number of the Catalan number is 1 over n plus 2n plus 1, because I have 2n plus 1 rotations times 2n plus 1 over n plus 1. And if you look at the formula, 2n plus 1 factorial over n plus 1 factorial n factorial, then of course, if we can rewrite this as 2n factorial over n plus 1 factorial n factorial, or 1 over n plus 1 to the 2n factorial over n factorial n factorial, and this is the formula that we proved before. So the tricky part is to prove this proposition. So if I circularly shifted these sequences, then I will have one and only one sequences that obtained from the correctly matched brackets. So you can think of this as, so maybe I will add some parts of it proof into the homework, or you can just think of it and prove it by yourself. Okay, do you have questions of this? So idea I think is clear, but how to prove it, it's maybe a tricky one, yeah? But of course, you have the rotation of this cube, and you want to calculate different colorings, but if the cubes are going to each other with the rotations, then it will be the same coloring. So you want to calculate all different types of colorings. And for these colors, it's not very hard, but if you, for example, say that there are only 5 colors, and so you have 5 faces will be different colors, and one face will be the same color as another face. Then it will be a little more complicated. And so this is the same idea. So if you want to calculate all like bracelets or something like that, so you have no bracelets. I just forget the, sorry. Necklaces. You have the necklaces, and you have like again different colors, different coloring of it. And so how much necklaces can you have if you have I don't know k different colors? Because if you rotate them, or maybe if you rotate and reflected it, it will be the same necklace. And so this is the same as this guy. So this idea of rotation, it's the same idea here. So if you want to calculate this guy or this guy, we'll need to use some similar tricks as the proof of this proposition. But of course, I just okay. I spent all the break I spent on discussing some non-important stuff. I don't know, do you prefer more combinatorics or more graphs in our course? Because we already spent like 4 or 5 weeks of combinatorics, and also we can discuss some different topics on the graph theory. So maybe we can stop here and just I know, again, if you want me, so if you want me to discuss some specific topics in graph theory, we can also discuss it now, because so in previous year I discussed Euler and Hamiltonian path, and planar graph, and maybe some I just don't remember. So you discussed Euler graphs in the first part of the course? What? Okay. What exactly do you know from? Okay. So you know only the definition.
Yeah, and there are some proofs. Yeah.
Proofs?
Like some condition that if you have the graph cannot be on the same length.
Sorry, what condition?
Yes.
What condition?
Some conditions like if you have your graph can be on the same length.
Okay.
And,
Okay. So okay, I will just so we can discuss, and we'll remind you all the statements that I can prove, and you say that you prove it already, or maybe you want to hear the proofs. And planar graphs? No. What do you do? What do you know from graph theory, except from, so you know the definition of graph, you know all about trees, I suppose. No? Trees? Yes. How much time do you spend on the graph theory in the first part of the course? Like half of the course? Yeah, but what you studied, so what do you know about graphs? Or you suggest coloring, graph coloring? No?
We had it previous semester.
Vertices edges. You have colored vertices, you have colored edges of the graph. Vertices. Okay. Okay. So there are many different topics, so we can discuss like Ramsey numbers, or some trivial facts about hypergraphs. So you discuss chromatic numbers. Okay. Hypergraph, we can discuss like Hall theorem. So this is about okay, maybe I will just need to remind you of it, and we will not we will going further. So what it called? By matrices of zeros and ones? Presentation of graphs by matrices? Okay. So we already discussed that we usually in combinatorics we have some sequences of an, and you want to say something about an. You want to find the formula for the n. You want to find the approximation of an, the upper and lower bounds for an. And if you don't have recurrence relations, linear recurrence relation, you can find, so you can find some easy relations, then you can look at these sequences as power series. So if you have A0, A1, A2, etc., AN, etc., some sequence, you can try to look at the function A0 plus A1x plus A2x squared plus A3x cubed, and so on, and try to say something or do something with this function. So you have some, so you maybe discuss this series in calculus. You can integrate it, you can take the derivative, you can multiply it by other sequences, you can try to see, try to find the, so the one of the questions is, for each axis this have sense. So is this series converges or will be non-convergent? So you can just say something about these functions. Will help you find the properties of sequences of sequence AN. So we need to discuss this guys called formal power series. Formal power series. And if you have the sequences, this is usually called generating function for sequence AN. So they exactly mean the same, generating functions and formal power series. So I don't know if how deeply we're speaking about polynomials. Because this is similar to the polynomials, except for you have infinite number of powers of the x here with non-zero elements. But the idea is the same. If you have so the formal power series is just the formal summation of these monoms. And if you have two formal power series, we can define the product and sum of two formal power series. So if you have started with f0, f1, x, f2, x squared, and so on, g of x is g0 plus g1 times x plus g2 times x squared plus so on. So we can define sum as if where we just take the linear combinations of the constants, and if you want to calculate the product of these two guys, we just take the same formula as we using when we're talking about the polynomial. So we can just imagine that we have two power series here, and then we just open the bracket and look what expression can we get. So if you want to calculate the coefficients before the x to the n power, we just take f0 times gn plus f1 times gn minus 1 plus etc. plus fn times g0. Of course, there is a little bit naive definition, because I already used the multiplication, and so I already used the sum and product in this expression, And so there is a question if my definition is correct, because I have two kinds of pluses here: the pluses of between the coefficients and pluses in the definition of my power series. It is the same problem if you look at the polynomials. You have the same problem. You can just say that you have so if you want to define formally the sum and product, you cannot use the same denotations here. So you just need to be clear about what you mean by this expression. Yes. So if you want to do this thing formally, so I can do it, but I don't think that it is necessary to. So it is the same as a polynomial. So if we can look at the formal definition, then we should start with the sequences and just define sum and product on just on the sequences here, and then define sum and product on the sequences, because we already understand that you can just say that formal power series is just the sequences which is expressed in some tricky way. Define plus and products on the sequences, and then we can denote by x the sequences 0, 1, and all zeros, infinite number of zeros, and just prove. So x squared by the definition of the product will be 0, 0, 1, and all zeros, and x cubed will be 0, 0, 0, 1, and all zeros. And so this is just the basis of this infinite dimensional linear space. So we have linear space of sequences. It is infinite dimensional, and so the basis for this linear space is 1, x squared, and so on. And so each sequences can be written as linear combination of these guys, and so this is just expression of this linear combination. I put it shortly because I think you maybe discuss this when you were defining polynomials, but I think if you so you just correct that, proves that the definition of sum and product are correct, but I think it is easily to see that it's okay for you to do this calculation of sum and product. So if we need to, it is very useful to describe the formal power series not using the infinite sum here. And one of the ideas of doing this is to express this formal power series into short way. So in particular cases, there is useful to use the inverse of the formal power series, and the definition is the same as always. So if you have fx is formal power series, then gx is the inverse to the f of x is if the product is 1. So we can write this as f of x is 1 over j of x, or j of x is equal to 1 over f of x. So for example, so let's start with a simple geometric progression. Can we find the inverse of this formal power series? Of course, the inverse is usually denoted by f to the power minus 1 of x if it exists. Of course, it will be if it exists, it is unique. And of course, my multiplication is commutative, so I can write fx times g of x is equal to 1, or g of x times fx is equal to 1. So I don't think I need to explain the definition. So how can I find the inverse to this formal power series? So someone has idea what the answer should be? Yeah. So if you take minus 1, I just take 1 minus x. 1 minus x. So if I want to prove it, I just need to calculate the product of this and check if this will be equal to 1. Is this correct? So which we can, so if you multiply by 1, that will be the same power series, and when I multiply minus x, then I can write this as minus x squared minus x cubed and so on. So if you summarize this, then I will get 1 here and 0 everywhere else. But how do you get the answer? You can just look at the definition of the product and then write the system of linear equations on the inverse power series. So if I denote this as g0 plus g1x plus g1x squared plus etc., then I can multiply by this formal power series and then write the system of linear equations. So I just multiply g0 plus g1x plus g2 squared and so on with this formal power series. So what should I get? I will get, so 0 coefficient will be g0 times 1, and this should be equal 1. The first coefficient will be g0 times 1 plus g1 times 1, and this should be 0. The second coefficient will be, so I need to write the full expression here. But my all coefficients of formal power series f is 1. So this will be just sum of the elements. And so if you for arbitrary n, then sum of first n coefficients will be equal to 0. And so from this equation, g0 is equal to 1. From this, g1 is equal to minus 1. From this, g2 is equal to 0. And from this equation, we will be also getting that gn is equal to 0. And so the answer is correct. And so we have the same answer as here. It will be 1 minus x. Just solving the linear equations. Okay, what is the necessary conditions of formal power series to be inverted? So if you have formal power series, then there exists f minus 1 of x if and only if f0 is not equal to 0. So if the coefficient f0 is not equal to 0, then we have f of x is inverted, has an inverse inverted. And if f0 is equal to 0, then it has no inverse. And the proof is not very hard to see. If f0 is equal to 0, then if there exists in inverse of the f of x, then g0 times f0 should be equal to 1, but f0 is 0, and so this equality is not true because of contradiction here. So we cannot multiply f by something to get 1, because we need to multiplication of 0 coefficients equal to 1, but our coefficient f0 is 0. So I prove that if this is not true, that this is not true. So I prove it from left to right. So if there exists an inversion, then f0 is not equal to 0, because otherwise we'll have a contradiction. And if f0 is not 0, then I want to prove that my system of linear equations has a solution. And this is not hard to see, because so if I want to find g0, then I can find it from the equation of g0 times f0 equal to 1. So g0 is 1 divided by f0. If I want to find it f1, then I can look at the second equation and find that g0 is, oh no, not g0, g1. G1 is minus g0 times f1 over f0. So g0 we already found earlier, and we also can divide it over 0 because it's not equal to 0, and so on. So we can find this by induction. So we can prove that Gn is equal to minus Gn minus 1 times f1 plus etc. plus g0 times fn divided over f0. So we can find all the coefficients of the inverse formal power series, and this means that this formal power series is invertible. Okay. Let me give you some 2 or 3 simple examples, and I think this will be all for today, because we need to make a test. And so the next lecture will continue in discussing formal power series. So we already find what is the inverse of the 1 minus x. Okay, let's have, so let's let's discuss in 10 minutes this reduction. So I want to find, by find I mean that you should express the formula for the an. So 1 over 1 plus x is inverse of the row of the formal power series 1 plus x, and so you just need me to express what is the an. So what is the coefficient? nth coefficient of formal power series. Like we want to, yeah. So we want to so this formal. So what is 1 plus x? 1 plus x is formal power series where all coefficient from the x is 0. Yeah. So this 1 plus x has this is invertible. So this is equal to a0 plus a1x plus a2x squared, and so on. And I want to find your an. What is an here? Or just find the expression of this formal power series. Okay? And the same for these two guys. Okay, need to prepare. Where is tasks for today? So you already know all the tricks here. All the down you remember from the calculus. Okay, but okay. So what is the answer here? What's the first coefficient? Something like this. Yes. So how do you get it? You can just take our previous example and then change x by minus x. So if you change x by minus x, then all even powers of x will be positive and odd powers of x will be negative. And if you want, for example, go to the 2 minus x inverse, okay, so you can just calculate. So if you want, just do it from definition of formal power series. I will rewrite this as half of the 1 over 1 minus x over 2, and then I just use the formula of the previous formula, but use the x over 2 here. So it will be 1 over 2, 1 plus x divided by 2 plus x squared over 4, and so on. So the coefficient will be something like x to the power n divided over 2 to the power n plus 1. And how do you get the last one? The last one, actually, you can do the two different ways. So the answer is this x n minus 1 plus 1 minus 1 minus 1.
Sorry.
1.
How did you solve the first one?
Okay, someone don't understand. Okay, the first one, I just change the x. I put minus x instead of x here. So all I need to do is just calculate it this guy, and so all the even powers will be positive and all odd ones will be negative. And how do you get this one? Because if you know it from calculus, then you can explain it from the calculus how to calculate it, but you don't remember. Yes. So if you go, so you have two possible ways. First of all, take the derivative of the 1 minus 1 over 1 minus x. So if you take the derivative here, then you will have 1 minus exactly this one. Because so there will be minus 1 minus 1, and so there will be this way. So you just need to differentiate the formal power series. But we didn't discuss it. But it's similar to the differentiation of the functions. You can just define the formal derivative as yes, f1 plus 2f2x plus 3f3x squared and so on, and prove that the formal derivative is satisfies the is linear and satisfies the Leibniz identity of derivative of the product, and then you can use all the formulas of the derivative like this one. And so if you take the derivative of this guy, you will if you have derivative of this guy, you will have this guy. But of course, if you don't understand the how to get the derivative, you can just calculate it just make the straightforward calculation. So 1 minus x in the power minus 2 will be 1 plus x squared plus etc. squared. Yes? And so you just can open the brackets and calculate that if we want to calculate the coefficient before the nth power of x, we just have the exactly n summations of ones, because we take this guy, again the same guy, and then if you want to calculate the coefficient before xn, you take 1 times 1 to the n power 1, 1, 1 here, and so we have n plus 1 is 1, so we will have n plus 1 times x to the power n. This is the same as this, but it is summarized from n equal to 1, and this is summarizing from n equal to 0. So okay, so you can maybe already on the answer, but you can calculate at home what happens if you have the arbitrary power k here. So what should I get here? And we'll use this formula if we're talking about the useful if you're talking about the partitions. Okay, times 1 plus x plus etc. Then the first coefficient will be 1. Then before x there will be 2, because we have 1 here and 1 here. 3x squared and so on. And again, if you have the derivative, if you take the derivative of xn is n times xn minus 1. So there should be different numbers here. N here and n minus 1 here, or n plus 1 here and n here. Okay?
X plus 2x squared plus 8q.
This one? You want to calculate the inverse of this one?
Something like that.
But it's not very hard. You can just write the. So if you want just. So this power series is not inverted because the zero efficiency is 0. But you can write the short expression if you just take the. So x plus 2x squared plus 3x cubed and so on. You can just take the x out, and so inside of the brackets will be this form power series. So we can write it as x over minus x over 1 minus x squared. So of course, if you have if your form power series has zero coefficient, then you can just take out the minimal power of x, and then the formal power series inside the brackets will have the invertible, and you can just write the expressions like this one. But of course, okay, my last remark that of course sometimes you cannot write the short expression. So of course there will be a formal power series with the infinite terms, infinite non-zero terms, with which has inversion has also infinite non-zero terms. But this is just the simplest example where we can find the inverse. But in arbitrary case, of course, there is no there is no such simple expression maybe. So you can just need to write this infinite power series here.